Hi guys, this is Vicky again, and today we are going to go through the 2015 AP Chem FRQ question number 1, and it's a redox type of question, okay? So let's get right to it. So question number 1, it says metal air cells are a relatively new type of portable energy source consisting of a metal anode, an alkaline electrolyte paste that contains water, and a porous cathode membrane that lets in oxygen from the air. A schematic of the cell is shown above. Reduction potential for the cathode and 3 possible metal anodes are given in the table below. So this table right here. And then early forms of metal air cells used in zinc as the anode. Zinc oxide is produced as the cell operates according to the overall equation below. That's the equation, and it says using the data in the table above, calculate the cell potential for the zinc air cell. Okay, so first of all, let's look. This is question A, and we are looking at zinc. The equation zinc O2, and it's becoming 2 zinc oxide. So based on this, we know for a fact that this is an atom and this is a 2+ charge, so that's a cation, that's an atom, and we're looking at that equation over here. And if you guys remember, okay, E cell is equal to E of reduction plus E of oxidation. Okay, so which one is undergoing reduction? And if you guys remember oil rig, I know some people memorize it as Leo Gers. I memorized it as oil rig. Oxidation is losing electrons, reduction is gaining electrons, but whatever floats your boat, you go for it, okay? So which one is undergoing reduction? So based on this, if this is becoming that, it's basically losing 2 electrons, right? And this is 0 charge, and that's a 2- charge. So this right here has gained 2 electrons. So oxygen is undergoing reduction, while zinc is undergoing oxidation, right? So in the reduction step, oxygen is right here, so 0.34 voltages, and oxidation, I'm just going to switch the signs, look at zinc, and it's right here, it's negative 1.31, but I am going to switch the signs because it's oxidation, okay? And if I were to add everything up, I end up with 1.65 voltages, and that is going to be my answer for A, okay? At least A1. All right, A2, it says the electrolyte paste contains OH- ions. On the diagram of the cell above, draw an arrow to indicate the direction of the migration of OH- ions through the electrolyte as the cell operates. So if we are looking over here, electrons are going towards the right, right? And the electrolyte paste essentially is supposed to be your salt bridge, right? So anions are always going to go the opposite direction as that of your electrons. So if I have OH- in the electrolyte paste, I'm going to go the opposite direction as that of the electron. So it's going to go to the left. Okay, that is just so that we can balance out the charges. Okay, all right. B says a fresh zinc air cell is weighted on an analytical balance before being placed in hearing aid for use. As the cell operates, does the mass of the cell increase, decrease, or remain the same? So let's look. We are going from zinc, okay, to zinc oxide. Zinc versus zinc oxide. Which one is heavier in mass? Zinc oxide is heavier in mass, right? In molecular mass, right? And therefore, as the cell operates, the mass of the cell will start to increase, okay? Increase. And for 2, they're asking you to justify that based on the overall equation. And basically, it's because zinc has more mass than the original zinc. Sorry, zinc oxide has more mass than just regular zinc. So zinc interacting with oxygen, okay, produces a heavier compound, okay, zinc oxide. And that's it. Alright, so now let's continue to C. And C says, the zinc air cell is taken to the top of a mountain where the air pressure is lower. Will the cell potential be higher, lower, or the same? Okay, so for instance, this is a mountain, right? And up here we have less pressure. That basically says that I have less oxygen particles. So if I have less oxygen particles, that just means that I am not going to maximize my cell potential. So therefore, it will be cell potential lowers, okay, will lower. Because I'm not using up all of the compounds in the chemical reaction, okay? All right, let's continue to 2. It says, justify your answer to part C1 based on the equation for the overall cell reaction and the information below. So all it's saying, it's this. It's just saying that, so if I were to have my equation plus oxygen, and I am making zinc oxide, okay, and let's just say that at a higher elevation, because I will have lower partial pressure of oxygen, I am basically going to have a lower amount of oxygen, right? Because oxygen is a reactant, so the partial pressure, it's just going to keep lowering it. So we know that zinc, here, these are all solids. This is a solid, this is a solid. So if I were to just look at, for instance, like Kp, it would be PO2, right? Q will also be PO2. But if you look at it, here at higher elevations, it will be lower, right? If it's lower, it just means that the equilibrium will decrease the magnitude of, as the cell goes closer to equilibrium, it will decrease the magnitude of the cell potential. Okay, cool. All right, let's continue to D. D says the metal air cells need to be lightweight for any application. In order to transfer more electrons with a smaller mass, sodium and calcium are investigated as potential anodes. 1 gram anode for which of these metals would transfer more electrons, assuming that the anode is totally consumed during the lifetime of the cell. So they're asking you which one is going to maximize the amount of the cell, right? So if I have 1 gram of sodium versus 1 gram of calcium, first thing first, always switch to moles, right? And about 23 grams of sodium is equivalent to 1 mole of sodium, right? And for every mole of sodium, I have 1 mole of electron, right? And so that is going to be 0.043 moles of electron that goes back and forth. Whereas 1 gram of calcium, if I have 1 mole of calcium, calcium's molar mass, it's about 40 grams of calcium, okay? And for every mole of calcium, I have about 2 moles of electrons, right? Because it's Ca2 plus, right? Okay, so that I end up with 0.050 moles of electron. So which one will create more electrons? Okay, obviously it's going to be calcium. So calcium would transfer more electrons. Okay, all right, let's continue to E. And E says the only common oxide of zinc has the formula ZNO. Write the electron configuration of zinc atom in the ground state. So if we look at the periodic table, super easy way to do this is just go, okay, like this. So what you're looking at is basically all of the elements on this side is going to be in the s orbital, including that, right? And all of the elements on this side is going to be in the p orbital. And then all of the elements on this side is going to be in the d orbital. And we just keep reading it this way. And if we read it, this is n equals 1, this is n equals 2, n equals 3. And then down here in the d orbitals, we just go down 1 step. So that should be n equals, we start out at n equals 3. Okay, so if I were to write it all out, it would be 1s2, 2s2, 2p6, right? I'm starting out over here. 1 is 1, 2, 2 is 2, 2p6, okay, 3s2, 3p6, 4s2, 3d10. So again, it'll be 3s2, 3p6, 4s2, 3d10. Okay, so that's how you would do the electron configuration. Alright, so that was part 1, and part 2 says from which sublevel are electrons removed when a zinc atom in the ground state is oxidized. So the most outer shell out of all of these is going to be 4s, because that's the 4th shell. Okay, so we are getting it out from 4s2. And if you look, so think of it as this. Imagine this is your nucleus, right? And this is your first orbital, your first shell. That's your 1s, right? And then you create a second s. Okay, so that is going to be your second s, 2s, right? But from here, you also create 2p. And inside this second shell, you create 2p. And the p orbitals, they look like dumbbells, right? So that's going to be 2p. And then from here, you create one more. Okay, and that is going to be 3s. And then from here, you create 3p, right? 3p. And again, we have 3 different types of p. So that's 3p. And then from here, one more, 4s. This is your 4s. But you look down and you're like, oh, the 3rd floor is still kind of empty, so we can actually like fill it up. So we're going to do the d orbitals that kind of look like this. And there's like 5 different versions of those that go in, right? This direction, and then one that kind of looks like this, right? And if you look, now the 3d is inside, and so the 4s is the most outer shell, and electrons from the 4s are going to be the ones that will be ripped out. Okay, hope this makes sense, and I will see you guys on the next video. Bye!